study at UC Berkeley, and he made a postdoctoral study in University of British Columbia. After that, he went to Courant and then Oxford, and now he's in Berkeley as a professor. He's interested in probability theory and rigorous theory for statistical mechanics. He's a Simon Fellow and Fellow of the Institute of Mathematical Statistics, and today he will talk about state-governed random term games. Thank you, Alan.
Okay, thank you, Adrian. It's a great pleasure and an honor to speak to you today. The dawn's just breaking here in this corner of the West, so I'll wish everyone good morning, Sharon. Good morning. I'll be speaking on state-governed random turn games, joint work with Gabor Petter of the Rennie Institute. This work is on the archive for a few months now. If I have to sum it up in one sentence, this concerns multi-turn games with an element of randomness in the way the decision about who wins each turn is made. And if there's an organizing question for the research in the talk, it's sort of, if you look at a position in a partially played game and you ask yourself both, how should I play next, but also what is the kind of strategic importance of the next move relative to the likely lifetime of the game and the later moves that may take place? What is that importance and how do we quantify it? Okay, so let me start with the context that I'll use. Geometrically, it's a simple one. It's going to be a finite graph, and it will have a certain boundary that I'll label in red, that's B. So let's begin simply with harmonic functions. This is a kind of a route into the topic. So if I have a certain boundary data F on the red vertices, I can consider the harmonic extension of that boundary data H. So that function is characterized by the property that if I consider the difference of H values along each edge in the graph and square that, raise that to the power of 2 and add that up, then H, the harmonic extension, is the function that has the property that that functional is the minimal subject to having the correct boundary data on the red vertices. We can say 2 harmonic to emphasize the fact that I'm raising to the power of 2 when I do that. And of course, we have the familiar formula that's easily seen to be equivalent, in which a function is harmonic if its value at any given vertex in the interior is equal to the average values at the neighbors. And that latter blue formula brings in probability in a natural way, simple random walk that begins at a certain vertex in the interior and jumps uniformly at random to a neighboring vertex at each step, can be stopped when it reaches the boundary, be at a certain time tau, and then the harmonic extension of this given boundary data F has the property that we can view it as the mean value for the walk beginning at this vertex V of the evaluation of the boundary data at indeed that moment when the walk does reach the boundary. Okay, so for purposes of emphasis, I can call X, that's naturally associated to 2 harmonic functions in this way, I can call it the 2 walk, if you like. Simple random walk is in this notation, the 2 walk. So yeah, using that language for other values of P, I can do something similar. If I take the difference in H values and raise it to the power of P and do the comparable minimization, I could speak of that as being the P harmonic extension of the boundary data F. For various values of P, could I consider that? That's quite a nice definition. That one can ask if there's a P walk for each value of P and so on. I want to focus on P equals infinity. And here we have the notion that H on the vertices, again, real valued function, is infinity harmonic extension of F if it coincides with F on the boundary, and if for each interior vertice, it has the property that the particular H value at that location is such as to minimize the maximum difference with the H values at the surrounding vertices. So in in blue on the sketch, you have the various values of H assumed at the neighboring vertices, and the value that HU wants to assume, therefore, is the red value, which is precisely halfway between the minimum and the maximum value, because that's how you're going to achieve the shortest distance to the furthest away H value of a neighbor. Okay. All right, so there's a nice formula for that. In other words, H is infinity harmonic if its value at each vertex is quite simply the average of the value, the maximizing H value on neighbors and the minimizing such value. So in terms of the conceit of the way I phrase this, the natural question is then, what is the infinity walk? Is there a natural stochastic process X that has precisely the same notion as before? Watch the walk until it reaches the boundary, evaluate the boundary data there, take the mean. Given that you started in a location, we want that to be H of V. There's I suppose a typo between U and V on that orange shirt. Let's say H of V should be equal to the value of this object when the process begins at V. Okay, is that a clear question? What's an infinity harmonic function stochastic process? So this brings in game theory. There's an oppositional character in that formula between maximum and minimum. So a counter in green begins at an interior vertex, and I have two players minimizing and maximizing roles, Mina and Maxine in blue and red. So what's going to happen is at each turn, it's a random turn game, and at each turn, a coin is flipped, a fair coin. The turn victor gets to move the counter to an adjacent vertex. Similarly, at each subsequent turn, the game ends when the counter reaches the red boundary B. At that moment, a payment pay is made from Mina to Maxine, which is equal to the evaluation of the boundary data F at the terminal location of the counter, the point on the boundary that it reached, okay? Yeah, so, all right, to tell you a bit about the connection and why indeed this is the infinity walk, I need some definitions from game theory. So a strategy in a given game, this game theoretic notion basically means a complete specification of how a player will play. So they see any given position, a strategy tells them what to do in that position. It could be a deterministic move, or it could be a random one. If it's a deterministic move, that's called a pure strategy. So the two players, in fact, they have exactly the same sets of strategies, formally speaking, in this game. Let me label them script S minus and script S plus. And for any given strategy pair, M of S minus S plus is equal to the mean value of the terminal payment made from Mina to Maxine when the game ends. Okay, so yeah, with that definition, we can speak of game value. So let's consider, as is common in game theory, the notion that one player is put in the seemingly disadvantageous position of being forced to declare their entire strategy to their opponent at the outset of the game. Suppose that it is Mina who is forced to do that. What's the best she can do in the sense of average value of outcome, given that she has to do that? Well, her opponent, Maxine, will exploit the fact she's gone and declared, say, S minus, and will take the supremum you see in the middle of this screen. Mina knows that Maxine's going to do that, so she takes the corresponding infimum. So the best she can do is the blue V minus. We could call it her game value, Mina's game value. Symmetrically, if Maxine is put in the position of declaring, then we see V plus instead. Now, it is indeed the case that it is not an advantage to have to declare in this way. And for this reason, V plus, which is what Maxine wants to maximize, V plus is less than or equal to V minus. Now, if the two values are equal, and they are not for every game, but if they are equal, then the common value is called game value. The game value exists, and the common value is the game value. So von Neumann proved a minimax theorem that shows a certain class of games have this value, and there was a sense when he did that that game theory was a theory, that the theory was beginning with that theorem. Okay, so all right, from Perez, Schramm, Sheffield, and Wilson in 2009, we have this theorem. I'm just focusing on finite graphs in stating this. On a finite graph, the game value does exist, and indeed it is the infinity harmonic extension of the boundary data F, which is the amount that Mina pays Maxine on the boundary. And under optimal play, Maxine moves to an H maximizing neighbor, and Mina plays to an H minimizing one. It's perhaps rather intuitive that the theorem holds given the average formula we saw earlier. I will be later giving a proof which is very similar to the proof of this. So I won't say more directly about the proof at this stage, but is that statement and connection clear? So this was a nice connection built by these authors in a wave of attention and interest that came into random turn games as a result of 2 papers they released around this kind of era 15 years ago. Okay, so as an aside, I should mention that Parrish, Shrem, Sheffield, and Wilson were interested in taking continuum limits, playing random tug of war in a Euclidean setting with small step sizes and taking a low epsilon limit and recovering a continuum version of the infinity harmonic function that's indicated here. It's a beautiful, delicate theory, and actually the directions I raise in this talk for state-governed games have very interesting interactions with the continuum. It's not nonetheless the focus of this talk, but I mention it as a signpost to that work. We remain in a discrete context for this talk. Okay, so I now reach the question that I sort of began in the intro. What is the strategic importance of a position in a multi-turn game? What do we mean by that question? Let's take the line graph with 2n vertices, call it L2n. Now, play is trivial here in terms of moves. Maxine moves to the right, Mina to the left, clearly, because the reward of 1 lies at the right vertex. 2n, $1 awaits Maxine if she achieves that location, 0 for her if it's the left. So suppose that at this very first turn, beginning at n, Maxine is offered the right to buy the first move, but the later game will just run as usual. It's a one-off thing. How much should she be prepared to pay to exercise that special right? If she does buy the first move, she's going to move the counter legally, as it were, 1 step to the right. And then you see her payoff at that point is just the linear interpolation of the endpoint values, because play is a simple random walk, 50-50 chances. So that means that her mean payoff is 1/2 plus 1/2n. Now, if she doesn't buy the first move, if she declines that offer, then the game just continues as usual from the original location. So in that sense, the payoff from there is 1/2. So her advantage monetarily is 1/2n. And that means the fair price of the purchase is 1/2n. Okay? So that seems, in a sense, a fairly clear answer to the question. Well, anyway, this is equally true for each starting position because the linearity of the value function. So the apparent conclusion is that all positions are equally important, and each one is worth of the order of 1/2n, of the order of 1/n, okay? 1/n seems to be the answer. It's a spatial prediction because it concerns the first move and where a Maxine goes, if you like. But there is another view. So under optimal play, we have the simple random walk counter evolution, and that game is therefore going to last order of n² steps. Now, if all of the moves are equally important and the total amount of money at stake is $1, then I suppose the first turn must be worth 1/n². So there's an inconsistency. There's a different prediction of 1/n² coming from this. Okay. So in summary, then, 2 different predictions about the importance of the first turn, a kind of a spatial prediction based on this first move buying argument of 1/n, and a time-based prediction about length of game that appears to predict the order of 1/n². Now, both of these predictions play a certain role in the direction of the talk, so they're worth just keeping in the back of mind. What I want to do is, in the middle section of the talk, is to tell you about a slightly different but related direction, and that's the game of Hex. So this is a 2-player alternating turn game. It was invented in 1942 by Piet Hein, and as a graduate student at Princeton, John Nash reinvented it and proved some theorems about it in 1948. Now, it's still played in tournaments, sometimes between computers, sometimes between humans, often on an 11-by-11 board. And I'm going to, as it were, define it, explain it by example. I bought a board, came in from France, and this is it. There's orange and green players. I'm going to explain it by running an example, really. I'm going to reenact the Computer Olympiad 2003 between 6 computer versus a mongoose, green against orange, okay? So, yeah, game 5, okay, of the Computer Olympiad 2003. Okay, so one of the players goes first in green. There's a slight oddity about the position of the first counter. Maybe let's not focus on that for the time being. The players play alternately, each player playing in an unplayed spot. The aim of the players is to forge a connection, a path, between their opposing color camps, green to green or orange to orange. It's a topological fact related to the Brouwer fixed point theorem that precisely one player can forge a connection on this lattice between their own color camps. So game continues in this way. I don't know if I will try to commentate it exactly. You do see this phenomenon of rubbing shoulders a little bit where the players play along a single path, and it's orange that is coming in for the kill there and winning with a connection between the opposite sides. So game 5 was a victory for Mongoose. Okay. So yes, the first turn there, there's a special rule that determines it. It's intended to offset a certain advantage the first player has. Perhaps it would be an aside to explain it in full. Okay, so one thing pairs Schramm, Sheffield and Wilson did was to consider a random turn version of this alternating turn game, but quite simply the victor at each turn is decided by a fair coin flip. Okay, so if we have, I'm going to go for red and blue colors. If I have a partially played position of hex, as you see here, I'm going to explain the game value after the game, and for that I need a definition. If I take a given unplayed hexagon, like the brown one here, I can define the H value, HP of that hexagon in the following way. So okay, so I can consider two new positions, one in which that hexagon becomes red, PV plus, and another in which it becomes blue, PV minus. For each one of those, I can fill in the rest of the board uniformly at random, red and blue, according to fair coin flips. Now, in the resulting outcome, red will tend to win a little bit more than blue does when I fill in the given hexagon V red rather than blue. Now, the quantity delta here at the bottom of the screen is the non-negative difference in probabilities of red victory, given that the rest of the board is filled in at random. Okay, it's the probability, in fact, that V is a pivotal connection when the rest of the board is filled in at random, in the sense that if its status changes, the victor of the game changes. So the theorem the authors proved is that if you take any partially played position in hex, the value of that position, if both players play optimally, in other words, henceforth, the mean value of the payment that Mina will make to Maxine at the end of the game is equal to H of P as just defined. And under optimal play, each player, if they're victorious, will select the unplayed hexagon V for which this pivotal probability as defined, delta, is maximal. Okay. Again, I won't, I think, prove that right now, but I will later on give a related proof. What I want to do next is show you some simulations, in fact, of random turn hex. Judith Zador, my wife, coded this in Python. In the first thing here, we see a 11 by 11 board with a partially played position. And what happens is that for something like 1,000 times, we fill in the rest of the board at random. We find in each realization where the pivotal hexagons are. We keep track of them. And then when we've done enough trials, we select the one that got the most votes, the one that's most likely to be pivotal according to a numerical approximation. So if I run this by one step, I'll just do it one step to demonstrate. It was selected that, in fact, the one that's most likely to be pivotal is that blue hexagon. I'll explain the other plots, the middle and right plots, as we go through some simulations here. So let's run a game here then. The first move is already played in these games. So you see red winning there. I should explain that red is playing left to right in these games and blue is playing up to down. So in the middle sketch, you see dynamically what the predicted win probability for the two players is. And in the right sketch, you see the function delta, the maximum pivotal probability in the unplayed board. So let's move up to a 15 by 15 board. So you see this sort of rubbing shoulders phenomenon that Piet Hein has defined it, in which the players sort of play along, tussle along a common route and try to control and dominate it. So red finally came through, blue finally came through and won that one. Let's go up to a 31 by 31 board. So you see fairly connected play most of the time. You see this dominance attempt to compete. So red now with a slight advantage, attempting to forge a connection over to the right here, blue trying to block that. Now there's a slight loss of interest in that, ended in a kind of draw, it's on hold, and blue is trying to surge in a north-south sense. That's the sense in which blue wants to build a connection. With some success now, blue building ahead on pivotal probability into the 80s now, trying to forge a connection north, and red now sort of behaving defensively, trying to block off this rubbing shoulders phenomenon at the south end of the board, continuing to do that for now, although still in a fairly weak position, but continuing to hold off. In fact, then getting some lucky coin flips to block blue on one side, and now trying to go more offensively, red surging through to, in fact, win the game, coming from a kind of a 15% kind of situation with certain weakness, coming back to win. So you see the maximum pivotal probability delta plotted dynamically has this build up to a kind of a crisis or peak in the 25 range, and then coming off again to a slightly less tense end game. Okay, so yeah, so let me say Piet Hein was, as well as being a mathematician, he was an inventor and a poet. Now, he wrote many poems that he called gruks, from the Danish grin uk suk, meaning laugh and sigh. Now, in early April of 1940, Germany invaded Denmark, where Hein was living, and Norway. And one in his first gruks the following week, in an edition of Politiken, which I believe was the publication in which 2 years later he introduced the game he called Polygon. In this edition, Hein addressed his fellow Danes with the following Greek, one of the first. The consolation Greek: you lose a glove and it feels like pain. What then if in losing one, you discard the other, only to find the first again? So let me move to now the direct definition in terms of the game we consider with Garble, which is a kind of development of random tug of war. A parameter lambda between 0 and 1, between 0 and infinity is given. The players are allocated budgets or fortunes at the beginning of the game, 1 for Mina and lambda for Maxine. Now what happens is, at the start of a given turn, some part of those fortunes remains to each of those players. And at the start of the turn, each is asked to stake some part of their remaining fortune. So suppose that this is a decision for the players. Maxine might choose to stake A and Mina B, okay? So these sums are then swept away from them, deducted from their respective fortunes, and never returned, neither during the game nor after it finishes. Now, Mina then wins the right to move according to a random decision, as in the random version of the game, but now with a bias. So the probability that Maxine wins is A divided by A plus B, the amount that Maxine stakes divided by the combined stake of the players at the turn. If Maxine doesn't win, Mina does. Now, the turn victor moves the counter to a neighboring vertex, just as in the classical version of the game. And then the next turn proceeds, of course, with the updated and diminished fortunes, and of course, according to the same rules. At the end of the game, as in the classic version, Mina plays Maxine, the F value at the terminal counter location. And the players lose any money that they have from their fortune at the end. So the role of the fortunes is to kind of regulate the game, not to act as a payment in real money as they leave at the end of the game. So two needed concepts in order to explain the analysis and ideas of this game. So one is a generalization of the infinity harmonic function away from the case where lambda is 1, which is what we saw before. The lambda biased infinity harmonic function that extends f has this formula that you see on the screen. It corresponds basically to the notion that Maxine wins each turn with probability lambda over 1 plus lambda, and Mina, of course, otherwise. Now, these functions can be computed by a certain path decomposition. Take the graph seen at the bottom of the screen, the T graph. It has 3 boundary vertices, and you see the vertices labeled by the values of f on the boundary, 2 interior vertices. Now, there's, as it were, 2 ways of filling in the values on this graph. On the left, I've indicated in bold, one could compute that north vertex interior by simply considering it to be the interpolation of the points 1 and 2, according to the direct formula you have for a line graph. And then you would go on to complete the graph at the south vertex, the interior vertex. Or you could work the other way and complete along the copy of L3, the line graph with 3 vertices that runs from the 0 vertex to the 2 vertex. And then there wouldn't be any other vertices to fill in. Now, the correct way of doing this in order to get the lambda biased function depends on the value of lambda. If lambda is less than the golden ratio, we use the method on the left. And if it's greater than that, we use the method on the right. I suppose both methods work in the critical case. Okay. So that was Paris and Sunich that introduced this decomposition in general. Okay, the other concept is a general one, of course, from game theory, Nash equilibrium. The 2 players have their respective strategies. A strategy pair is a Nash equilibrium if neither player benefits from unilaterally deviating from it. That's basically what the meaning of those inequalities is. We measure their benefit by mean expected receipt, okay? So it's a fact, not hard to prove, that at any Nash equilibrium, the payoff, mean payoff, when the players play at the Nash equilibrium, exists and is equal to the value of the game. The value of the game exists and is equal to the mean payoff at any Nash equilibrium. Okay. Okay, say dream wild game value. Under a certain hypothesis, I want to advocate a certain point of view about the state-governed game as it's been introduced. So we have a delta function that's similar to the one we saw for hex, of the maximum minus the minimum value of the lambda biased function on vertices neighboring the given vertex u. Okay, let's suppose that that function is positive at all the interior vertices of the graph. That's a fairly minor assumption. More importantly, I want to assume that there's a pure Nash equilibrium. That's a Nash equilibrium in which the players play deterministically. Specifically, they do not make random stakes in response to seeing the board counter location. They make deterministic ones. Okay, so then what I claim is, under that assumption, the game value exists, and it is equal to the lambda biased infinity harmonic function extending f. So in that sense, the state game is a kind of enhancement of, or something that projects onto the original tug of war game with a lambda bias. Okay, is that statement clear?
Alan, can I just ask, so do we imagine them declaring their stakes simultaneously, or do we imagine one player having a strategy that's declared and the other one responds to that? Or how do the stakes get declared each turn?
Well, it's in the nature of the definition of game value that if it exists, one player, the players will end up with the same outcome if one player declares their entire strategy beforehand. I think there is a detail about whether the players decide where to move, having learned what the other player state was. There's a particular choice that's made for that.
Because it doesn't seem obvious. Maybe this A on plus B makes it work. Because if you had a general probability based on A and B, it's not obvious that having to declare your stake first wouldn't be a disadvantage, right? Or is that somehow true for all sorts of forms of P of AB?
Yeah, for definiteness, let's say that in the rules of the game, the players declare at the same time. Just provides a simple answer to the question, which perhaps slightly ignores its underlying meaning. Now, in terms of, it is a non-trivial proof that game value exists in the game. So that is something that then means that if one player is forced at the beginning of the game to actually declare what their entire strategy is, it isn't on average disadvantageous to them.
But does that proof use the form of the probability is A on A plus B, or would it go through fine for any reasonable, if I make it A squared on A squared plus B squared, will it still?
I think it's probably that the proof is rather dependent on the structure, because it's a detailed reduction via this kind of observation to the biased harmonic function case. Yeah, I'd have to think though about that offline a bit to see if maybe I suspect it does depend somewhat on that. Yeah. Okay.
Thanks.
So the reason that I'm assuming there's a pure Nash equilibrium, it means that if one player, it basically permits strategy stealing in the sense of, well, this proof. So suppose that there's an equilibrium that is pure. That's what's indicated at the top here. So what Mina can do is develop a strategy that's very much based on learning what S plus 0 is and kind of mimicking it or stealing it. Because under the pure strategy S plus 0, the point is Maxine is going to stake a given amount at each turn. So what Mina can do to react to that is to develop a strategy in which she stakes the same deterministic proportion of her remaining fortune at each turn and proposes quite explicitly to move to an H minimizing neighbor here, where H is in fact H lambda comma dots. It's the lambda biased infinity harmonic function, and lambda is the initial relative fortune in the game. So by doing this, what she can do is force a game in which she wins each turn with probability 1 over 1 plus lambda, and that will remain true consistently. Her relative fortune will remain what it always was. And this has the effect that the resulting, if we monitor H lambda xi as the game develops along the counter evolution xi, this is a bounded super martingale in which if Maxine is failing to move to the H maximizing neighbors, its value on average drops a little bit. So its value is in the mean dropping towards its terminal value, which is just the terminal payoff, because it's easy to see on a finite graph that the game will almost surely end in finite time with Mina playing in this way. If she wins a sequence of moves, she'll win. Yeah, okay, so that has the effect that the mean value under this strategy pair, S minus strategy steal against Maxine's component in the pure Nash equilibrium, is at most H of V. Now, S minus 0, S plus 0 is itself in equilibrium. And so this means that, in fact, the mean payoff under the Nash equilibrium is at most H of V. But you can consider that argument symmetrically for Maxine to learn the opposing inequality. Or I should write U, sorry, instead of V at the bottom there. So we proved by that, by strategy stealing, that the mean value at the Nash equilibrium is equal to the H value, the H lambda value, in fact, where lambda is the initial relative fortune of the players. And that is sufficient to prove that the value of the game exists and is equal to the infinity biased harmonic, lambda biased infinity harmonic function. Okay? So that's a conditional result that is provoking, and it prompts two questions. Notably, does, of course, a pure Nash equilibrium actually exist? Now, if you admit that, it leads to another question, which is, well, okay, that means if it does, what's going to be happening is Maxine's fortune is, if it's lambda times mean as at the beginning, or at a given situation rather, if Maxine's fortune is lambda times meaners, and the counters at a certain location, what we've learned from the preceding proof is that the players will in fact be staking a shared and non-random proportion of their present fortune. So if we call that S lambda V, that's a stake function. So what is it? And this question speaks to the strategic importance of the position, because relative to the rest of the game in a certain sense, a kind of question I was mentioning at the beginning of the talk. Because you see, the money that you have has to be sort of budgeted throughout the rest of the game. It's all very well winning the next move with a big spend, but you need more money to make convincing bids later at the game. So the stake function captures a sense of the importance of the particular move you face relative to the gameplay at large. Okay, so I want to give a kind of what could be called a plausible argument that identifies the stake function. So suppose Mina has fortune 1, that can be made the case by currency evaluation. So if Maxine has a lambda fortune and the counter's at a certain location, and we abbreviate the stake function under the hypothesis of pure Nash equilibrium, this capital S object exists. So therefore, under optimal play, Mina will be staking a proportion S, Maxine likewise, which means lambda S is the money she stakes. So let's do a perturbation argument and consider instead the possibility that Maxine deviates to bid very slightly more, tiny bit more, represented by this addition eta to her expenditure in essence. If she does that at the first turn, but then plays optimally later, let's consider the implications for her of doing that. So there's a gain or a loss by doing that. So basically the gain arises because she spent a bit more, she's more likely to win the first turn. So circled in orange there is in effect the gain in probability of Maxine winning the first turn because of her deviation in behavior or extra expenditure. And circled in red is the benefit she gets by doing that. She wins the first move. She plays to an H maximizing neighbor rather than losing out and going to an H minimizing one. So we have this sense of a gain turn. Now, there's a loss turn though, because at later turns, she's got a tiny bit less money consistently. Her relative fortune is indicated here, and it has the effect, it's a bit like Rousseau's formula for percolation, if you like. There's at each subsequent turn, there's a tiny chance of losing it because of the deformation you made earlier and the less money you have. And that's represented by taking a mean over the lifetime of the future evolution of the game of the delta value. That's the consequence of losing a later turn, multiplied by an outside term that reflects the probability that you actually do lose a subsequent term. I don't expect every thing on this slide to be crystal clear, but I'm hoping the overall concept is clear. There's a gain and a loss term with roughly these forms. Well, exactly these forms, I hope it's roughly clear why. Now, under optimal play, G is actually equal to L, because otherwise Maxine would indeed choose eta to be suitably positive or negative and small and exploit the imbalance. So the fact that G is equal to L using those previous formulas leads to a formula for the stake function, in which we see a ratio of terms, in which in the numerator we see something that earlier I called the space prediction. It reflects the short-term benefit of spending now. And then the denominator represents the pain later of having had that extra expenditure, a longer term consideration. And it's not unrelated to the time prediction from earlier. It's a kind of a form of the time prediction with a weighting for the spatial importance of the later positions. That's the formula you get. Now, this is still predicated on the existence of a pure Nash equilibrium. There is an alternative form of the formula in which the denominator is replaced by a partial derivative in lambda of the biased infinity harmonic function. This is basically a view of space, numerator versus money and denominator, short term versus long term. Do you want to spend big now, win upstairs, but suffer problems with less money later, represented by a denominator? So the tensions are represented by the forces in the opposing directions. Okay. Now, that's all very well. It's a plausible picture. It's not a proof. And there's two problems with it. Quite simply, for some simple graphs, as I'll show, there is no pure Nash equilibrium. So the entire structure might collapse. And secondly, for some other simple graphs, there's a failure of differentiability in this simple function, the lambda biased function. Okay, so very simple to illustrate problem one, no pure Nash equilibrium. The line graph with 3 vertices and the counter at location 2, Maxine's relative fortune equal to 1/2. Now, if a pure Nash equilibrium existed, we could explore the consistency of the picture by considering the possibility that Maxine bids a certain amount A and Mina B, because then under the assumption of the pure Nash equilibrium, given the proposition, we would be in a perfect position to plot the kind of conditional gain value that results from those decisions. And that's what's plotted here. This is kind of a contour plot of what happens in response to Maxine playing an X coordinate of A for stake at the first turn and Mina a B coordinate, a Y coordinate of B. These are best response curves for the two players, given what the opponent is doing. There's quite a lot to take in. The basic point is that the saddle point prediction coming from the formula we've seen is the yellow cross, and I would be expecting to see a nice contact and kind of a transversal crossing of best response curves if it were true. There is a local saddle point there, but it's not global, because Maxine in that territory is tempted to go for broke and bid everything. That's why her best response curve is over on the right. So, okay, I'll summarize that again in a moment. But problem 2 is that quite simply, the lambda bias function may not be differentiable. And that is indicated by the T-graph. The Paris-Sunich decomposition, as we saw earlier, switches as we move through the golden ratio between filling in values first on the copy of L2 at the top, and then switching at the higher lambda values to fill in a copy of L3 that runs from vertex 0 to vertex 2. And then, although H lambda V as lambda varies is certainly continuous through this transition, it's perhaps not surprising, given that this is the case. We're doing some sort of minimum or maximum of two simple functions, which I haven't written down, but they are simple. Well, the individual functions are continuous, but the minimum or the maximum operation on them isn't. So there's a failure of differentiability of this function at the golden ratio. So that causes problems, because we had this nice formula that we thought we derived, in which the denominator has can be expressed as a lambda derivative of h, but that's not even well defined, it seems, at all lambda values. So in one, there were two formulas. In one view, it's because h isn't regular enough, it's not differentiable in that example at the golden ratio. And in the other view, one can have a game theoretic view of things using the other formula. Basically, Mina has a certain strength and subtlety in a position that the north vertex is indicated here. She can play the short game of playing to 1 and closing out the game, or the long game of playing down to the south interior vertex, continuing the game, the long game. And she can force different gameplays by proposing different moves. So when it's all very well speaking of the gameplay process in that second orange you see in the middle of the screen there, but there are quite different processes with different values for this function, which should have a mean in it, different values for the mean of that quantity. So it's badly defined. So these are problems for this theory as it's developed. So in summary, then, we've got these two problems. One is that a player may be tempted to go for broke, as Maxine was from vertex 2 on the line graph 3, the best response curve over on the right, wanting to finish out the game. So that means a red cross only locates a differential little neighborhood with a local saddle point, but it fails to be global. And secondly, yes, quite simply, the lambda biased infinity harmonic function path decomposition switches, causing a lack of differentiability in the relevant function. Okay, so structure next, two modifications to overcome this, and then a positive theorem that does, in a certain context, rigorously set up the theory that we're sort of aiming for. Okay, so two modifications. One, to address the respective concerns, we will make the game leisurely, in a sense I'll define it, and we will restrict attention to a class of graphs I'll define in a moment, called the root reward trees. Okay. Leisurely is like the concept of laziness for a simple random walk. I introduce a parameter epsilon in green, strictly bigger than 0 and less than or equal to 1. And it joins the other parameters we have. The relative fortune at the beginning is lambda, the initial location is v. The rule change is players continue to stake at a given turn, but then what happens is after they've done that, the casino flips a coin, its bias to heads, its probability of being heads is epsilon. Now, what happens if the outcome is heads? The turn proceeds as it would have done originally. If it's tails, though, no move will even take place. The money the players have brought in is swept from them by the casino, and no counter move takes place. Okay. Now, the original game is when epsilon equals 1, because then the move definitely takes place according to the usual rules. And if epsilon is close to 0, then the vast majority of the turns, no move takes place. Okay. So the idea of basically introducing this was that low choices of epsilon should disable the efficacy of the go for broke strategy. I mean, just ask yourself the question, would you bet your house on the next turn, everything, if more likely than not, the coin will flip and it will land tails what you stake will simply be swept away from you. There's a sense of the long term becoming more important on the relevant time scale as we move to the leisurely game at low values of epsilon. Now, this is one of these normal form contour plots like the one I showed before, concerning what the two players do at the first turn for stake in the limit of low epsilon. There is a nice game one can try to define formally when epsilon is 0+. It's kind of a Poisson form of the game. But briefly, there is this is the prediction made before, appropriately interpreted with the yellow cross. And you see, this is the generic picture. I haven't explained what the graph is, but somehow this is the generic picture you get for these plots when epsilon is 0+. It's nice, smooth, and it's a global saddle point nailed by the yellow cross prediction, which is coming from the proposition we saw in essence. Okay, so modification 2, overcoming lack of differentiability in H as a function of lambda. Root reward trees. A root reward tree is quite simply a finite tree in which the boundary is the sets of leaves. One of those leaves is distinguished, and the boundary data is the indicator function of that particular green leaf called the root. So the key fact here for us is the Paris-Sanish path decomposition of a lambda biased infinity harmonic function on a root reward tree. That decomposition is independent of lambda. Let me show you a sketch. So here I have a tree over on the left. You see the green vertex there. There's a certain order in which you fill this in. The other leaves you see are indicated with zeros because that's the value of the boundary data. The value of the boundary data at the green R is 1. So we fill it in a kind of we fill in the shortest, lowest diameter subtrees first and go upwards in that statistic. And you can see that by identifying certain leaves and getting a simpler essence tree on the right. It's 1, 2, 3, orange, pink, green for doing that. Now, the point about that is that we do that in terms of a subtree diameters. We decide the decomposition, that's the right one. That's got nothing to do with lambda. Lambda doesn't enter into it. So the Paris-Sanish decomposition is independent of lambda for these trees. Okay. All right. So that then leads us to the theorem with Garbon. And you can see this on the archive. It's state-governed gains and the biased infinity Laplacian on the archive. So gain value and Nash equilibrium for the leisurely state game on root reward trees essentially says, making these modifications, I get the positive aspect of the theory. So yeah, what have I got then formally? On a root reward tree, I take any compact subset and then I consider the possibility that the relative fortune at the beginning lies in that subset. And for each compact subset, there is an epsilon k such that if I put my green parameter epsilon between 0 and that value and play the leisurely game with this parameter value epsilon, starting at the vertex V, we have the conclusions that the game value exists and equals the value of the lambda biased infinity harmonic function at V. Moreover, there are Nash equilibria, and at every Nash equilibria, the players play the H lambda maximizing and minimizing moves in terms of where they want to put the counter. And moreover, their stakes, well, for Maxine, it's lambda times S, and for Mina, it's S. And S is in essence given by either of the two formulas we saw before. The only difference is that it's kind of natural that the stakes are the epsilon multiple of what they would have been in the original context, because it takes 1 over epsilon steps to even see a move. So you expect the order which you stake to be of order epsilon. So simply multiplying the old formulas by epsilon to slightly oversimplify, we get the formulas in gray here. So yeah, that's the theorem there. So with appropriate modifications, this positive theory is advocated. And to return to the theme of strategic importance of position, in a sense, the state-governed games are a way of monitoring that. And we find these interesting formulas, I think, in which, in a certain sense, actually, it's the ratio of the spatial prediction and a certain variant of the time prediction that is actually measuring the strategic importance of the game according to the stake function value in gray here. Okay, there is a caveat though. There is a hypothesis that's also sort of important to actually get that theorem to work that's not stated there. The payment that Mina makes to Maxine, if the game never ends at all, plays for infinite time must be the full amount $1. Otherwise, there's a slightly odd phenomenon that can occur, and it does occur on line graphs, I think, of length perhaps 5 or larger. The formulas predict that Maxine will bid really very little and become a little bit complacent when she's one step away from winning. And this becomes a more extreme effect as her wealth rises. So this means that Mina is able to kind of use a kind of weakness is strength kind of strategy in which she actually deliberately loses money and throws it away when the game gets a turn away from finishing, and otherwise she basically stakes nothing. So she's actually able to keep losing money, and actually ironically forcing Maxine to spend less and less one step away from the end. So she wins the turns one step from the end but loses the other one. The game never finishes. She has to be discouraged from doing that by being penalized by the full amount in the event of a non-finishing game. It's a detail, but in a certain sense an important one. Yeah, so that's what that slide says. So yeah, there is a whole other view of state-governed games I did in independent work last year. I'll just mention it in 1 or 2 slides. Self-funded games. The fortunes were limited that the players were given to make them precious resources that the players must spend or hold back during the likely lifetime of the game. Now, there is another way of making a resource valuable to someone than limiting it. You can just say, spend your own money. Think of the players as being quite wealthy. Money's no real object to them, but they have to spend their own money. So you see, then the stakes that the players offer up during the game acts as a kind of a running cost that depletes whatever terminal payment or adds to the burden of whatever terminal payment gets made at the end of the game. So this naturally regulates things, so you don't need to limit the budget anymore. On the Trail of Lost Pennies is a paper I wrote about this. It has a very interesting and rather distinctive structure with non-trivial behavior even on simple line graphs such as L6, and quite a rich behavior on Z. The game we've talked about and ran in term tug of war doesn't really make sense on Z. This game does and is quite non-trivial. It has 3 Nash equilibria, I think, on L6, and it has countably many of them on Z. I don't have time to describe this, but here's just a sketch. This picture, in some sense, reflects the 3 Nash equilibria, different aspects of them, top, middle, and bottom, on L6 for the self-funded version of the game. And then I can't really say much about what the meaning of these lower sketches is. It is, I think, kind of fun, kind of a little bit cool that you have these rather exotic functions that appear. They represent a certain aspect, each one of them, of the game on a finite line graph. And then the index of the line graph is rising, the length of the line graph is rising as you see extra bumps appear. So, and then that leads to a limiting picture on Z in which this function wobbles up and down. The X coordinate in some sense represents Nash equilibria, the Y coordinate a certain aspect of relative payments at the end. Not time to discuss, but it is far from PDE applications, but it is a very distinctive, discrete, I think, rather interesting theory that poses interesting questions. So there's that paper out there as well. So our players have been in their competition in their zero-sum context. So I end with an image of, I hope, rapprochement between our 2 players.
Thank you very much, Alan. It was a very nice talk. Are there, maybe it's time for one question? Is there a question from the audience?
I have maybe a quick question. Maybe you said this before. So you discussed, like, on the T graph some of the problems with figuring out with the strategy of figuring out what the stake was, right? But it seems a small enough graph that the game should be fully analyzable. So does the Nash equilibrium exist, or is there a game value for that, or what can you say about optimal play and the game value in that particular game?
This is a very good question. Indeed, a very simple graph one would expect to be able to analyze it. We kept a fairly strong focus on moving towards the positive results. So in fact, this remains unanalyzed. Okay. It's a good question. it's an interesting related question. You see, in a sense, this phenomenon of going for broke and it being tempting would seem to be a very local phenomenon near the boundary of a graph. I mean, it might make sense if you're one step away from the boundary, but presumably not otherwise. So you would have thought that on a large line graph, generically in the middle, this wouldn't be a problem. But conceptually, it is a problem because the fundamental technique in game theory that we're using is backwards induction. And so you have to start one step from the boundary. So that step will be somewhat invalidated by this consideration, not just on this graph, but I think on any line graph in the unleisurely version of the game. So that effect may, in some sense, attenuate and diminish as you go into the interior, but conceptually it invalidates the inductive method of backward induction. It might be that the effect diminishes, but you have to analyze it in the right way. But indeed, it's a perfect graph to start with, this one. L2 doesn't work, but L3 already has this rather odd rich behavior. And I don't know the answer to your questions. They're very good questions and a good route, I think, into the topic to analyze them.
Yeah.
Thank you very much. So thank you, Alan. That was really nice. Maybe we take, well, we take help. And we take maybe 2 or 3 minutes to change the slide, and then we continue with the next talk.
Thanks, Adrian. So I pause share, is that the right one? Stop share.
Thanks, Alan. That was a really lovely talk.
Okay, so it seems that we are ready for the next one. Should we wait a couple of minutes, Alberto, or you think it's fine?
We can start, I think, or we can.
Yeah. Okay. So thank you very much, Taylor Helmuth, for being here and for presenting the next talk. So Taylor did his PhD at the University of British Columbia, and then did postdocs at the University of Bristol and the University of Berkeley. He's now an assistant professor in Durham University. His interests are in probability theory, statistical mechanics, and related algorithmic questions in theoretical computer science. And today he will talk about the arboreal gas. Thank you very much.
Okay, thanks a lot for the opportunity to speak here. And please, anyone interrupt at any time with questions. I have to say that I've been lucky enough not to have to teach online for some time, so I apologize for any poor slide work here. Okay, so the idea is to give you a bit of a survey about this object called the arboreal gas, which my working assumption will be that you've never heard of before this talk. And this is based on joint works with Roland Bauerschmidt, Nick Crawford, and Andrew Swan in a couple of configurations, but I'll also talk about some other recent work by other authors that it's inspired, and also some stuff that predates what we did. Okay, so by way of background, let me tell you 1 or 2 things about a much, in some sense, better understood model, which is bond percolation. So in bond percolation, which I'm always going to denote by this p tilde subscript p, every edge in your graph is occupied with probability p and 0, 1 in an IID way. So I think most of you have seen this before. So just to hammer it home, though, you have some particular graph, and this is one that I've drawn here, and you just pick for every single edge, okay, well, that one's in with probability p, and maybe that one is in, and so on. So it's just an independent choice at every edge. And people have studied this in extreme detail, I would say. So why have people studied it? And I want to comment on this because we'll have a few different contexts coming up. So one motivation that people like here, of course, is mathematical. And here I'm thinking about things like what is a random graph? So you could start with something like the complete graph and choose all of the edges to be in or out with probability 1/2, and that would give you some sensible model of what a random graph looks like on n vertices, and you can ask about its properties. Another motivation comes from physics. And often if you take here a first sort of introductory talk to percolation, people will say the physical motivation is that you have some material, like maybe coffee grounds, and you want to know, depending how finely you ground the coffee, does water pass through it? Does it percolate through? To some extent that is a motivation, but actually I think that's not really the one considered so much in the physics literature. I think usually what people want to know about is actually something called gelation or vulcanization. So what is this? Forgive the typo. What is this? You're supposed to think that every vertex in your graph represents a basic unit of some type of, it's a molecule maybe, or an atom. And they're in some solution. So you imagine you have a bucket and you dissolve some things into it. And you think of the edges that are present as being chemical links between those. And the question then is that you're forming some random polymer, the connections between all of these constituent units. And you want to know, do they form a big network that sort of ties the system up, or are they sort of separated from one another? So this is actually something that you probably understand. Depending on the country you're in, you use a different name. So if you talk about it where I come from in Canada, then or the US, you think of it as being jello. So you take the packet of powder and you dissolve it in hot water, and it behaves like a liquid initially, because the high temperature means that these bonds are relatively rare. But as it cools down, the bonds become quite likely, and they form this dense network meshing together, and you get a solid. So in some sense, from that point of view, the percolation phase transition is one of forming a gel or jello. Okay. Good. So that's a little bit of definition of percolation. I'm going to say more about percolation to come, but first let me tell you what the arboreal gas is, just so that we have the subject of the talk at hand. It's somehow extremely easy to define in a way that doesn't tell you why you would be interested in studying it. So what you do is you take the bond percolation measure you have on your favorite, let's say, finite graph, and you just condition on the event that all of the edges that you put in form an acyclic subgraph. So this means that this would be an allowed configuration. There's no cycles of green edges, but I couldn't also have that edge. This would include a cycle. Okay. And I'm going to use this notation for the arboreal gas, P sub beta. So when there's no tilde, it's the arboreal gas. And I have this change of parameters that beta is related to P in terms of this formula. And the reason for that is that if you look at this thing I wrote on the right-hand side, all this means is that the probability that you see some particular forest F is proportional to beta, to the number of edges in the forest. That's a little computation that you can do. If at some point you don't like the talk, there's a computation you can do to check that. So from this point of view, what's the question? How does this conditioning change percolation phenomena? Does it change percolation phenomena? And immediately you can sort of see that it's possible that it does. This is an extremely singular conditioning to do, to the point where percolation we can define on an infinite graph, no problem, because it's just independent on every edge. But this conditioning makes no sense on an infinite graph, at least if the graph contains cycles everywhere, like say Z2, because around any plaquette in Z2, there's a chance that you occupy all of those edges. So you're going to do it somewhere. So you're conditioning on an event of measure 0 in infinite volume. So on finite graphs, this makes sense, but it's a singular conditioning. And you really do have to consider the possibility this will really change what happened. In terms of phenomena, though, at least from the physical point of view, it's very similar why you might want to study this. And in fact, that's one of the first places where this was considered by Lubensky and Isaacson. And they said, well, what if you have some type of molecules where they're only allowed to bond to one another in such a way that no cycles are formed? And there are molecules of that type. And you can ask, is there a gelation transition for that type of molecule? So one thing from that point of view that's good to observe is that there's no giant if beta is small. And that's because you can stochastically dominate the arboreal gas by the corresponding percolation configuration. So you can always see that the arboreal gas is contained in a percolation configuration. So if the relation between beta and P is such that P is subcritical for the percolation, there's no giant. And the reason for this domination is just that the event that you're acyclic is a decreasing event. So this is the FKG inequality. But if the reason for this domination is not clear to you, don't worry about it. It's just a fact that there is some regime of beta small, when there's not very many edges in the forest, that all of the components will be small. Let me give you a slightly different motivation, maybe for this object, which is that you can ask what happens if you make beta very large. Well, on any finite graph, what you're going to get out is going to be the uniform measure on uniform spanning trees of the graph, at least if the graph is connected. Right? Omitting any edge becomes too expensive as beta goes to infinity. So you get this uniform spanning tree measure, and uniform spanning trees, of course, have been studied a great deal over the past, I guess now it's about 30 years since the work of P. Mantle originally. So one point of view is that you take percolation and you restrict the configurations to be ones that are forest, but the other point of view is that you take the uniform spanning tree and you relax the constraint that you're a spanning tree, and now you have this richer class of object. And both of those points of view are interesting and give you some, at least weak intuition. And another remark is that, as I said, in infinite volume, this doesn't make sense because it's a singular conditioning. So I think all I want to say now is that the infinite volume limit is subtle. In part because monotonicity in beta or the boundary conditions is not known. So unlike for the uniform spanning tree, where in some contexts you can unambiguously say what you mean by the infinite volume uniform spanning tree, that's not the case here. We don't know if you can do that or not. So from my point of view, that's perfectly fine because I'm mostly working from a rather classic equilibrium statistical mechanics point of view. I'm just going to always work in a finite graph and try and prove statements uniform in the size of the graph as that graph approximates, say, the CD. So what I want to do in the talk is to compare percolation and the arboreal gas and tell you what may or may not be some surprising phenomena. And in particular, I want to mostly tell you about some open problems or problems where alternate proofs would be quite interesting. And, you know, along the way, I'll give you some hints at methods. But I'm mostly trying to give you sort of a survey of what's happening. I'm not trying too much to talk about methods. So probably mostly I'll leave that for questions if there are. Okay. Any questions about the model definition or anything like that at this point? Otherwise, I've done something wrong. Okay. So let's start where things are the simplest, the complete graph. So on the complete graph, you know, I have n vertices. I'm denoting it by capital N here in the slides. Then percolation is just what's usually called the Erdős-Rényi random graph. And if you want the graph to not be super dense, meaning at a typical vertex, you only see sort of a reasonable number of edges, not diverging, you have to choose P to be something like alpha over N. So this is the correct scaling of the percolation probability. And there is a phase transition for percolation in this setting, and one way to summarize it is to write the following. This is a theorem. If I take the expectation of the size of the component containing some fixed vertex 0, so I look for the connecting component containing fixed vertex 0 and ask how big is it, I get 3 different behaviors depending on the size of alpha. So there's a subcritical regime, alpha less than 1, where the expected size is sort of order 1. So this slightly bizarre notation is cases inside of the order notation. So this is of the order of. In the subcritical regime, you're order 1. In the supercritical regime, alpha bigger than 1, you're of order n. And right in between, when alpha equals 1, something more interesting happens and you're size n to the 2/3. Okay, so this is separating regime where there's all these tiny islands. There's one big island and something interesting, the critical component. So I'm not so interested in the subcritical regime in this talk, and what I'm really interested in is the supercritical regime. So what are the important features here? It's the case that there's a unique giant and it occupies a positive fraction of the graph and of order n. And moreover, the second biggest cluster is actually of size log n in the supercritical regime. Sometimes this is called the discrete duality principle. But the way that I want to phrase it is that off giant is subcritical. So it's the case that the expected size of the component containing one vertex is of order 1, but the biggest component you see in the subcritical regime is of order log n. And that's what's happening in the supercritical regime. If you ignore the giant, then you see something that's comparable to the biggest one in subcritical. Okay, so let's compare to the arboreal gas. This was studied by Wuchek and Patel, I think basically motivated by saying, well, what happens if you do this conditioning some time ago? And what they proved initially is that, well, again, you should scale beta like alpha over n if you're on n vertices. And they proved a very similar result if you look at the size of the tree containing some fixed vertex. They showed that its expected size is order 1 in the subcritical regime, which again is alpha less than 1. It's of order n if alpha is bigger than n, and is of order n to the 2/3 if alpha is 1. So it's exactly this picture, or very nearly. Again, there's the unique giant, but there is a big change, which is that if you look at the kth biggest cluster, other than the giant in the supercritical regime, it's not of size log n. Instead, now it's of size n to the 2/3. So instead of going off of the giant and seeing something subcritical, you go off the giant and you see something critical. So off giant is critical. And they did this by fairly explicit computations. And you can really say just about everything you want to at this point in time, because there's a further result by James Martin and Dominic Yao, and they compute the full joint limit of all the non-giant components essentially. So this is the analog of Aldous' theorem for the Erdős-Rényi random graph. So it's the case that you really do see something interesting and critical happening off of this giant component, at least in the complete graph set. Okay, so what happens once geometry comes into play? So then we're sort of in the subject, or for me, I'm going to say geometry for me is going to mean the Euclidean lattice, ZD. So let's first remember what happens for percolation. So one thing, we should restrict our attention to 2 and higher dimensions. Otherwise, nothing much interesting happens on the line. If you independently include each edge, it just disconnects into pieces. But in 2 and higher dimensions, there's a critical percolation probability, PC, such that as long as you're away from the critical percolation probability, if I ask what's the probability 0 is connected to some other vertex x far away, then it's basically equal to some quantity theta of p squared plus an exponentially small correction. So this is probably not the way you've usually seen the percolation phase transition. So let's just say what these terms mean quickly. So theta of p is something that you may have seen. Theta of p, well, it's 0 if you're below the critical value, and it's something positive if you're above. So what this first term is saying is that if you're below the critical probability, then it's very unlikely that you're connected from 0 to x if x is far away because of this exponential decay. While if theta of p is positive, what it's saying is sort of that you have, what's the probability 0 is connected to x? Well, it's sort of like you have 2 independent chances to be in the giant component. And otherwise you have some exponentially small correction to that independent claim. So I should write down that there's a unique giant, and it has density theta.
May I ask one question?
Yes, please.
Thank you. How does this compare to random cluster models of FK type?
Right, so percolation is the random cluster model with Q equals 1. And the arboreal gas is in some sense the random cluster model with Q equals 0. But interpreted correctly.
Oh, thanks. Thanks.
Yeah. Okay, so this first term tells you about the fact that there's a unique giant and what its density is. And the second term says that off the giant is subcritical in some sense. You really, if you're not in the giant, meaning you see the correction term, it's this exponentially decaying connection probability. So the biggest clusters you'll see are sort of log the volume. I should say I wrote theorem here, but this theorem is really many theorems by many authors. So Eisenman, Barsky, Eisenman, Keston, Newman, Burton, Keene, Chase, Keston, Grimmett, Schoenman, and Grimmett Westrand, I think are the main authors you need to put this together, but there could be some missing from that list. Okay, so it's from the point of view of that theorem that I want to tell you what happens for the arboreal gas on ZD. So first theorem is that something dramatic does happen with this conditioning. If you look in 2 dimensions, the arboreal gas has no phase transition. There's never a giant tree. So this is the informal statement. The formal statement is this. You choose whatever beta you want. So in principle, this is supposed to tell you there's as many, the density of edges is sort of getting towards its maximal value if you take beta large. You take any subgraph of Z2 that you like, and let's say that 0 is inside of it, so that our question is going to make sense. Then there is some constant C that depends only on beta, not on lambda, the domain you've chosen. So that the probability that 0 is connected to X in the arboreal gas is actually polynomially small in the distance from 0 to X. So one way to interpret this, or one thing that this implies, is that no tree can have positive density. So this is very different than in the percolation setting where there is an infinite component and it has density theta of P, which is positive. Well, here, no positive density tree in 2 dimensions. Okay, so that's 2 dimensions. I should say, because I've used this abbreviation here, that was joint work with Roland and Nick and Andrew Swan. And then a little later, together with Roland and Nick, we thought, well, what happens in 3 and higher dimensions? Then there is a phase transition. So this absence of a phase transition is very somehow profound effect of the conditioning is a 2-dimensional phenomena. In 3 dimensions, the phase transition returns. So let me make the theorem more precise again. So for this theorem, our methods are heavier and we have to put some additional constraints on. So we're going to work on a specific approximation to ZD. And that approximation is that we look at tori of side length capital L to the n. So capital N is just controlling the volume of our approximation. And we're interested in what happens when n is large. And we also take this capital L parameter to be large just to make some technical things work. So we're looking at tori of side lengths of power of L and 3 and higher dimensions. Then our result says that if you take beta very large, so beta greater than some beta naught, then there are some parameters, kappa, which is going to be an error parameter, a theta of beta, which is the analog of theta of p from before. They're not the same function. And there's some other constant, c of beta. So that if I ask what's the probability 2 distant points 0 and x are connected in the arboreal gas on this torus, well, it's equal to theta of beta squared minus a term that's polynomially small in the distance, not exponentially small, plus 2 error terms. And the important thing is that I've taken beta to be large, so this should be the analog of the percolation probability, so it should be close to 1. And indeed, that's true. Theta of beta is actually equal to 1 minus order 1 over beta. And this slightly strange constant c of beta, when I've also put beta here in the denominator, is that this, again, we can give an explicit expression for the leading term that's independent of beta, and then there's an error. Okay, so again, let's try and interpret this formula a little bit. So I've just rewritten the formula here. So the third and the fourth terms, let's not talk about too much. They're just errors. So one error is saying that there are further corrections in terms of the distance between 0 and x. And this error is saying there's an error to do with the size of the torus. So we're working on finite tori. And there is some finite volume effect, but it's small in the diameter of the torus. The first term says that positive density trees exist. On a finite torus. And in the infinite volume limit, it would tell you infinite volume trees exist. And again, you can sort of think in some sense that this says you sort of, if 0 and x are connected, how does it happen? It's sort of like saying you have 2 independent chances to be inside the same giant tree. And then there's some correction term that corrects from being independent. Now, because of this sort of Gaussian type exponent, it's very tempting to interpret the second term as saying that off the giant is critical. Just because we usually associate this Gaussian behavior with critical behavior. So it's nice that I can tell you some very explicit consequences due to a very recent paper of Noah Halberstam and Tom Hutchcroft that I think was just posted on the archive maybe 2 days ago, or maybe it was at the end of last week, I forget exactly. So they were interested in studying what happens on all of ZD instead of a finite torus. And what they showed is that for the arboreal gas, in actually quite a lot more generality than this, but let me just tell you the result in ZD, they showed that there's at most 1 infinite tree for any translation invariant limit on ZD in dimensions 1, 2, 3, 4. So as a corollary of what I told you before, we learned that in dimension 2, there's no infinite tree. which is a slightly stronger statement than the zero density statement I made before. And in dimension 3 and higher, there's a unique infinite tree if beta is bigger than beta 0. Sorry, let me correct that because that's wrong. If d equals 3, 4. Okay, so actually this resulted on no infinite tree we knew before by other means, but their methods are much more robust and apply to other two-dimensional graphs. Okay, any questions at this point about the results before I give you a sort of lengthy list of open questions? Okay, so let me tell you one open question before I go to the sheet of open questions. And that's prove either of the two theorems I just told you using probability. So it's not to say that we don't use any probability, but parts of our arguments are fundamentally non-probabilistic, and it would be very interesting to know probabilistic proofs of these statements. But here are some other questions. So one is that for the uniform spanning tree, it's a famous result of P-mantle that in 5 and higher dimensions, the infinite volume limit of a uniform spanning tree actually becomes a forest. It disconnects into infinitely many infinite components. And based on that, it's very reasonable to think the same thing will happen for the arboreal gas. So the connections in take longer and longer to get, and you don't have continuity, so the connections will be lost in the infinite volume limit. But this seems to be difficult to prove. There's some discussion of this matter in Tom and Noah's paper from the other day. Another question is actually an old conjecture from the combinatorics literature, which is to show sort of a negative correlation property. So the conjecture is that on any graph, if you take two different edges E and F and ask what's the probability that you see both E and F, it should be at most the probability that you see E times the probability that you see F. And one reason this would be of interest is that it would tell you that a lot of different infinite volume limits are translation invariant. And then you would be able to apply the theorems of Noah and Tom about infinite trees. And also it would be nice just to know that the limit exists without having to take subsequential limits. So it's the case that actually you know this is true if you put a 2 on the right-hand side. This is actually relatively involved work of people who are studying algorithms and matroids. So Jun He and Peter Brandon and Nima Anari and co-authors. But the 2 makes it probabilistically not particularly useful because it's not a statement about monotonicity. And it would be very interesting to get rid of the 2. But it's been open for some time. Another question is that maybe you notice some hesitancy in my voice of saying the off giant is critical on ZD. The statement that I wrote down is a little, we'd like to interpret it that way, but it's quite far from saying something geometric about the trees themselves to say something about the 2-point function, the connection probability. I am fairly certain that this is correct in some settings, and there's some evidence of this by other authors. So one is the complete graph result that I mentioned before. There we really know geometrically that off the giant is critical. It's also the case, so these are theorems independently of ISO and of Rai and Shao, that if you look at this graph called the deregular wired tree, and you study the arboreal gas on that, so this is that you take deregular tree up to k levels, and then you identify all the vertices at the kth level together. That's called the wired tree. And that puts some cycles into the graph. So this arboreal gas conditioning of percolation has an effect. They show that the supercritical phase is made up of 2 types of clusters. One type is a critical percolation cluster, and the other type is the infinite incipient cluster of percolation. So somehow there are critical objects and there are infinite objects. The infinite objects are not unique anymore because of the tree structure. but you do see this criticality off the giant. So they're sort of strong heuristics in terms of what happens, at least for ZD in high dimensions, that off the giant is critical. But it seems actually to be the case that this is probably not true in low dimensions, in quite an interesting way. So there are simulations done by Chen and Deng, unpublished at this point, I guess. They're sort of preliminary. But they suggest that in 3 dimensions, there's a giant tree, but then the second biggest tree is polynomially big, but not the same size as the critical ones. So somehow this seems to be in high enough dimensions, you can expect off the giant to be critical maybe, but probably not in say 3-4 dimensions. Maybe it changes at 6. It's not super clear. It's not so easy to understand how to make a prediction about that theoretically, and the simulations are not so easy to carry out either. So it would be very interesting to understand that better. But to give you some idea of how incomplete our understanding of some of these phenomena is that we don't even know that the existence of an infinite tree is monotone in beta. So our theorem said that there's an infinite tree as long as beta is large enough, but our estimate of beta 0 is, has nothing to do with the truth, and we don't know that this is actually a monotone property. So this conditioning does really bad things to the monotonicity properties of percolation. Okay, let me give you one more open problem, and this is probably the most important one. And it's that the theorem that I told you in 2 dimensions, that there's no percolation because of this algebraic decay of the connection probability, is actually, it should be very far from the truth. The truth should be that the probability 0 and x are connected in 2 dimensions is actually exponentially small in distance to x. And even this constant in front for the decay is itself supposed to be exponentially small in beta. So I'll give you some idea of where this prediction comes from in a minute. It's sort of an analog of a very famous conjecture from mathematical physics and theoretical physics. So this would be fascinating. It seems to be quite challenging. Any questions about the questions before I tell you a little bit about methods/explanation? Okay. So I'm going to tell you roughly where this is coming from. Let me say, I hope I convinced you that there's some things that are surprising from the point of view of percolation. This absence of a transition in 2 dimensions, this algebraic correction instead of exponentially small in 3 and higher dimensions are sort of very surprising from the point of view of percolation theory. And what I want to first tell you is that they're actually natural from a different point of view, and that's the point of view we use in our proofs. So I'm going to do it by analogy, though. So there's something called the ON spin model. And what this means is that you look at functions, sigma, from the vertices of your graph into the sphere Sn minus 1, where n is at least 2, so that I actually have a continuous sphere. N equals 1, the 0-dimensional sphere, that's the well-known Ising model where you just have 2 points. But here I'd prefer to think about the relevant thing is when you have a continuous symmetry, so where you actually have at least a circle, but even better is that you have a 2-sphere or higher. So you can put a probability measure on all of those configurations, where the probability, is proportional to exponential of this Hamiltonian function h, and then there's some a priori measure, which is product uniform. Okay, so you integrate with respect to product uniform on the sphere pointing into the spin pointing into the sphere at every vertex. And then the interaction is that you sum over all the neighboring vertices beta times the inner product of the spins. So this is going to be largest if all of the spins point in the same direction, and making beta large is going to make that preference stronger. So you might wonder, do most spins point in the same direction or not? So for the Ising model, this is when you see a picture, and if beta is very big, you see all plus spins or all minus spins, and if beta is small, it's roughly a 50-50 mixture of the two. So this ON spin model has been very well studied, although it's still poorly understood in mathematical physics. So a first theorem, which comes from the physics literature, but it's a rigorous argument due to Merman and Wagner, is that if you take n to be at least 2, so you're talking about spins taking values in the circle or 2-sphere, 3-sphere, so on, and you're in 2 dimensions, then if you look at the spin-spin correlation, inner product of the spin at the origin with the spin at the vertex x far away, then this actually decays polynomial. So this is exactly like the result I said for the arboreal gas in 2 dimensions. Okay, the meaning of the left-hand side is different, but the thing on the right-hand side is different. As a remark, if it's the circle, the truth is that it's polynomially decaying. That's a famous theorem of Froelich and Spencer. That's what's known as the Kosterlitz-Daldis phase. If n is 3 or higher, then the conjecture is actually the right-hand side should be exponentially decaying. This is a conjecture of Polyakov. So the motivation from the point for this conjecture is that it seems to be a simpler analog of the Clay millennium problem about the Yang-Mills mass scale. So the Yang-Mills problem seems to be astonishingly hard. We don't know how to solve this easier version, and maybe the arboreal gas should be even easier, but it still seems to be difficult. Okay, that's 2 dimensions, and in 3 dimensions, this ON spin model, so n at least 2, d at least 3, beta big enough, then this spin-spin correlation is bounded below by a positive constant. So that means all of the spins tend to point in the same direction, because you take the inner product between any 2 of them, no matter how far apart they are, and you still have a positive value. So this is the theorem of Froelich, Simon, and Spencer. A pretty celebrated theorem, I guess. And the key difference so how should you think about this? If you've never seen a Merman-Wagner theorem before or thought about a continuous spin model, you should think that you pick a direction to order in. So it's a symmetric system, so you just pick whatever favorite direction you want, and you want to say, can the system order in this direction? Then the fluctuations, if you imagine you're ordered, then all the other spins should be pointing close to the same direction. So this inner product actually gives you something that looks like the Gaussian free field to do with the perpendicular fluctuations. So the perpendicular fluctuations from your chosen direction roughly have the law of the Gaussian free field. This is not a rigorous argument, but it gives you the intuition that makes the rigorous argument work. But then you use what you know about the Gaussian free field. That says that the variance of the fluctuations are infinite in 2 dimensions, but the variance of the fluctuations are finite in 3 and higher dimensions. So in 2 dimensions, if you assume that things sort of point in the same direction, you learn that the fluctuations about that direction are enormous. So somehow your assumption was incorrect. That's why there's no order in 2 dimensions. The proof that there's order in 3 dimensions is somehow a little more complicated, but this argument gives you the idea that it's at least possible that there would be order. Okay, so this says that if you have this point of view of spin systems from statistical mechanics, these theorems are not so surprising, and the connection is the following. There's I think, a brilliant observation of Caracciolo, Jacobson, Solur, Sokol, and Sportiello, which is that there is a spin system whose correlation functions exactly encode connectivity of the arboreal gas. So what that means is that if you want to study things like what's the probability two vertices are connected in the arboreal gas, you can translate that into asking what's the correlation between two spins in this spin system that they found. And the reason for the phenomena is that this spin system that they found, it has a continuous symmetry, which is very similar to the one that you see in the O3 model. So the behavior that's surprising from the point of view of percolation theory is in fact completely natural from the point of view of spin systems, once you know that behind the scenes there's this miraculous mapping. I shouldn't even say mapping, it's not quite a mapping, it's a, well, you can prove the identity of certain correlation functions. Okay, this is the point though where you could say, well, why did you tell me about the O3 model? And why do you say there is some spin system? Why don't you just tell me what the spin system is? So I'm still not going to do it quite yet. Let me just tell you by analogy again. So you should think that, let's think of S2 is solutions to this equation. So there's another spin system that people have considered called H2, which is where you replace the sphere by a hyperboloid. So x squared plus y squared minus z squared is -1, where z is positive. So this is called H2 because it's actually the hyperbolic plane, if you think about the natural geometric structure that you get. And okay, so this actually turns out not to be the most interesting spin system. And the one that's relevant for the arboreal gas is sort of an exotic cousin called H02. Where I'm just going to write, it's the same as H2, but you have to replace the real variables x and y with anti-commuting ones. So this is something known as Grassmann variables in mathematical physics. So given the time, let me make a few comments and then I can come back to saying what that is a little more precisely if people want. So the model is defined in terms of Grassmann variables and Grassmann integrals. And these are well understood things in mathematical physics. They're actually very nice to work with. It's much easier than standard measure theory. You just have to be a little bit careful about signs. It's a sort of non-commutative probability. But as with other non-commutative probability theories, there's some downsides. There's no notion of a realization. So this H02 spin model, there's no sense of saying, where does the spin point at vertex X? That question doesn't make sense. You only have a notion of expectation. So you only sort of have identities between, say, correlation functions, expected values of correlations, and connection probabilities. And maybe the bigger downside is that some analytic tools disappear. So for example, you don't have Cauchy-Schwarz for this Grassmann integral in general. And that's rather inconvenient if you want to, make estimates. So maybe let me just conclude by telling you what sort of the key tool is in 2 dimensions. And somehow in 2 dimensions, we want to make some estimate about a correlation decaying. So we really do want something like Cauchy-Schwarz or other inequalities. And the way it works is the following. So I want to have a Laplacian on my graph. So the Laplacian applied to a function f on the vertices is just defined by the usual formula. You sum over all the neighbors, beta xy, f of y minus f of x. These beta xy's are now weights on edges that depend on the edge. And the reason I want that is because I need to tilt those weights by saying if I have some function on vertices t, I define the tilted edge weights by multiplying my original ones by e to the tx plus ty. Okay, so now there's a scary formula on the page. Let's not worry too much about all the details, but what Roland, Nick, and Andrew and I have showed is that if you have any finite graph, any two vertices, 0 not equal to x, then you can compute a formula for the probability that 0 is connected to x. It's a standard integral. At every vertex except for 0, you have a value t. At 0, you set the value of t to be 0. And then you have, some integral. So there's sort of an a priori measure at every site, e to the minus 3t. There's an e to the tx, which is singling out the x. So here we singled out 0, and here we singled out x. There's some interaction between the spins. It's hyperbolic cosine of ti minus tj. And then there's some horrible term that I've hidden here at the end, which is the determinant of this tilted Laplacian raised to the power 3/2. Okay, I think it's fair to say this formula is not obvious. The benefit is that if you want to understand this object, on the right-hand side, we have an integral over this real valued field t, and the tools of analysis become available. While if we were working with the system I talked about before, with Grassmann variables and integrals, we don't have analysis. So just a couple of comments about this formula, and then I'll stop. One is that this integrand, it's not obvious at first glance when you first see it, but it actually has a symmetry inside of it. It's invariant under shifting all of the t's by a constant, if you ignore the fact that we've fixed t0 to be 0. So this is a shadow of the continuous symmetry of H02. And that's what lets you run a Merman-Wagner argument. And actually, the Merman-Wagner argument is not so complicated because Christoph Sabot developed an argument already for a very similar integral in the context of something called the vertex reinforced jump process. You might wonder why that's related to this integral, and that's a slightly different story. Again, to emphasize that it would be nice to have probabilistic proofs, our proof of this ends up being rather roundabout. We have to go from, one, the miracle that you have this H02 representation of the correlations or the connection probabilities. Then you have to go to a slightly more complicated model that I don't want to tell you about, but it's defined similarly, called the H24 model. Then you have to choose coordinates in a clever way to get to this T field, which is a sort of marginal. And then you run a Merman-Wagner and you get polynomial decay. But it's quite indirect to go from a probability model, the arboreal gas, through two different, somewhat non-standard spin models. This one has, 5 variables. Take a marginal to only down to 1 variable, and then run another argument. So a direct probabilistic understanding of how to get this would be, of interest. I think I'm out of time though, so let me just skip that slide about 3 dimensions and say thanks.
Thank you very much for the nice talk. Are there questions? Yeah, Sarai, please.
Oh, hi, Tyler. It's nice to see you.
Hi.
Thank you for the great talk. You mentioned that one needs to be careful with the infinite volume limit. And you mentioned something very briefly, and then you stated your theorems for the torus. So I was wondering what happens if you consider other boundary conditions.
So the short answer is that for other boundary conditions, we can't say anything formally.
Oh, okay. But that's a short answer, so there's a long answer.
Yeah. Of course, I think everything that I said is true for, say, free boundary conditions, or for that matter, probably with wired boundary conditions as well. But because our methods rely very much on being able to decompose a torus into blocks and having every point look the same, you would have to do a substantial amount of work. And then, there's some very interesting questions, but the argument, either the renormalization group argument, where people are sort of only, I think, just beginning to technically understand how to approach having a boundary being present. It adds really a lot of complication.
Nice. And sort of related, you mentioned that the theorem that Noah and Tom just uploaded to the archive is requires translation invariance of the limit. So
Yeah.
do you think that you're setting that should be true, or where that should be true?
I think all the it's a little risky, and so in 2 dimensions certainly they all should be. In 3 dimensions, for things like the Ising model, you have these examples of non-translation invariant Gibbs measures. It's hard to see how that would happen here, but so one thing I would say is that I do believe that this conjectured correlation inequality is true, and that would tell you that every free boundary limit in ZD would be translation invariant. So at least for those, it should be true, but it's hard to know what's lurking out there, say in 17 dimensions for strangely constructed Gibbs.
Yeah, well, thank you very much.
Hi, Taylor. Can I ask, perhaps in regard to the monotonicity question, if one edge is in the arboreal gas, the conjecture is that another one is slightly less likely to be in it. If one considered a Glauber dynamic, just the ordinary dynamic on percolation, and then at each step just cancelling the move, basically, if a cycle is created, and then you take 2 copies, one of which is further conditioned on insisting that a given edge be in, then I think probably it doesn't quite work, doesn't have the relevant monotonicity.
Right. Yeah, so it's sort of, you lose the coupling once you you can sort of hold the coupling up until you sort of might create a cycle for the first time. Once you start to break the cycle, in some sense, you lose the coupling. Okay, I guess all I can say for that is that when I've thought about this approach, it doesn't seem to yield monotonicity because you lose the coupling.
Yeah. Okay.
Is there another question?
I also ask just 2 questions. Thanks. Hi. So great presentation, and 2 questions. Firstly, could you say anything about the scaling limits in this context? You didn't mention this specifically, but could these objects be studied in this context? And you mentioned for the H02 and possibly H24, the non-commutative probability aspects. How do you come to this? And could it be translated to free probability? Is there a relationship or, yeah, thanks.
So let me answer the second question first. So this connection to non-commutative things was first discovered by these people I mentioned, Caracciolo, Jacobson, Sokol, Sportiello, and Salur. There it is. They thought about it as being related to a version of a sphere, actually, and somehow the thing that Nick, Roland, and Andrew and I realized is that it's better to think about it as being something hyperbolic. How they found that is by a very clever application of the matrix tree theorem, and thinking about that in terms of anti-commuting variables. So that theorem says that if you want to count spanning trees in a graph, it's equal to a determinant, and a determinant is how, in some sense in physics or theoretical physics, people think of a determinant as being an anti-commuting object coming from some fermionic variables. So for them, that was a natural way to rephrase things, and they found the connection in that way. The hyperbolic language is useful because that's where these very nice coordinates, which are key in our 2-dimensional result, come from. And the importance of those were found in the context of yet another model called the H22 model that was studied by Margarita Dissertori, Tom Spencer, and Martin Zirnbauer. So for us, it was useful to make this connection to hyperbolic language because it gave us access to these coordinates. In terms of a connection to free probability, I think I was just trying to draw an analogy that this is sort of like a version of non-commutative probability, but I don't see any way in which those tools are useful here, but that's probably due to my large ignorance of free probability. I can't say anything to it. Your other question was about scaling limits. So there has been work on saying what it means to have a scaling limit of things like the uniform spanning tree by Eisenman, Burchard, and so on. So in some sense, there is the type of object and framework to understand what that would mean here. But at this point, we haven't thought about that so much, I think is the short answer.
Okay, thank you. Thanks.
Well, thank you very much to Alan Taylor. This was really nice. So thank you.
Thanks.
And with this, we finish today's session, and we meet again in 2 weeks. I hope that many of you can come again. That's it. So maybe you stop the live transmission, Alberto.
So, Adrian, shall we just meet at like 3 o'clock and 10 minutes beforehand?
Yep, perfect.
And then you
I
will
will-
be free tonight for a drink and pizza and so on.
Great. Yeah. I will use my iPad if that's okay for the talk. That works?
Yeah, of course. Yeah. Yeah. Mhm.
Great. Okay, see you later.
Okay.
Thank you very much. That was really nice.
Okay. Bye-bye.
We are still live in YouTube.